this session, let us look at the circular convolution, one of the important properties of DFT. Let us look at what is circular convolution. Let us solve some problem. Circular convolution. Let us start with the circular convolution now. Understand the circular convolution. Let us first take two DFTs. Let us say the length of n, okay, and then let us multiply them. Okay, if these two are multiplied, okay, let me call the product of these two as x3 of k, which also is a DFT. That means, let us say this is also DFT. Okay, that means I am multiplying two sequences of length n, okay, of DFT, and the product is also a DFT sequence of length n. So, this is what we are saying. Now, let us find out the inverse DFT of this, and let us call that as x3 of m. Okay, x3 of m. Let us see what is the equation for this. So, this is given by summation n is equal to 0 to n minus 1, that is the length of the sequence. Then this will be x1 of n, that is, this is the inverse DFT of x1 of k, x1 of n. Then x2 of m minus n, okay. So, this is the mod of n. So, this is what is the circular convolution. Now, if I compare this with a linear convolution is just shifting and adding, isn't it, the product here. So, but here there is a little extra here. What I was doing is a modulus n here. So, this we call it as a circular convolution. In other words, circular convolution means the product of two sequences in DFT will result in a circular convolution. So, how do I express this? So, let us say x1 of n and x2 of n. These two are circularly convolved. So, I put a letter n here and I put a circle around it. So, this is an indication of circular convolution. This will be equal to having a DFT, okay, which is nothing but x1 of k and x2 of k. So, this is our property of circular convolution. Let us see one small example on circular convolution and try to understand how we can do circular convolutions. This is an example 1. See one example. We have to perform the circular convolution for the given sequences. X of n is given, x1 of n is given, and x2 of n is also given. So, what are the steps to be followed in calculating circular convolution? First is, we call the first step as folding, or it is also called as a time reversing. Second point is, okay, shifting the folded sequence. Third is calculating the product, okay, or multiplication. Let us say this is multiplication, then followed by summation. Okay, these are almost the same steps which we follow in a linear convolution. Same here also, we have to do some folding, that is time reversal, then shifting the time reverse signal, that is the folded signal, then product or multiplication of the signals, then comes the summation of it. So, these are the 4 steps involved in the calculation of a circular convolution. Let us also make note here the formula which we have studied earlier. For circular convolution, x3 of m is given by summation n is equal to 0 to n minus 1, x1 of n, okay, multiplied by x2 of m minus n of module n, okay, of modulus n. I correct. I read this, x3 of m is equal to summation n is equal to 0 to 1, x1 of n, x2 of m minus n module n. So, this is the formula. Let us do circular convolution for this. Let us start with the drawing. So, what we do here basically is, we represent this in the form of a circles. So, we will take a circle, in that circle we make points here. So those points we are putting it, marking on it. So as this is a 4 point n, what is sequence length here? And sequence length is 4 points. So we'll plot them on a circular graph and then we shift it, then we multiply and then we'll get the product. Let us see how it is done. Okay. Now first of all what we do is, we will plot both x1 of n and x2 of n. Then each case we will find out what is x3 of n. So this is what we are going to do. Okay. So let's start the first diagram. So let us first plot x1 of n. Okay. And x2 is the shifted signal. So let us look at x1 of n first. So let me draw a circle here. Okay. This circle I'll call it as x1 of n. Okay. How many points are there? x1 of n, if you see here, this is 0, 1, 2, 3. That's the 4 points. So n is how much here? N is 4 here and also n is 4 here. So let's start plotting them. So while plotting, we do what? We plot it in the anti-clockwise direction. That's what we are following here. So let us say this is my x of 0. So how much x of 0 here? 2 here. Similarly, what is x of 1 here? 1. This is x of 2, this is equal to 2, and this is x of 3 equal to 1. This is what we have plotted in the first case. Similarly, let us also plot for x2 of n. Okay, let us plot first here. Okay, this is x2 of n. We follow the same here. So this is x2 of 0, this is equal to 1. This is x2 of 1, that is equal to 2. And this is x2 of 2, this is equal to 3. And this is x2 of 3, that is equal to 4. Okay. So we have plotted in the anti-clock, whatever is there, we have plotted in the anti-clockwise direction as you see here. So let us just recollect what we have done. So I have taken a circle. On the circle I am marking points which belong to, so two circles we are drawing here, x1, x2 of n, out of which, as you see from the equation, this is what we are trying to fold and then trying to shift this. Okay, so folding, shifting and all those operations we are doing on this, because this is what we are saying x2 of m minus n. So we have plotted here all the values here, this is what it's done. Now the next job is, I have to find out what is x3 of 0, isn't it? So for that, when m is equal to 0, this x1 of n will remain same, whereas x2 of it will become minus n. Okay, so it is minus n. So let's draw a circle here, and then I call this as x2 of minus n. Now what I do here is, to calculate x2 of minus n, what we do here is, this is in the anti-clockwise direction. Now I make this clockwise direction. So this is my x2 of 0, that is equal to 1 here. So whereas this will be now this, that is x2 of 1 is equal to 2, then followed by this x2 of 2 is equal to 3 here, and then this is x2 of 3, that is this is equal to 4. Clear? So what is it we have done here? This x2 of minus n, this is in the anti-clockwise direction, this I made it in the clockwise direction. Now we have to product or get the product of x1 of n and x2 of minus here. Okay, so let's do this here. What is the product? So this I call it as x1 of n and x2 of minus n. Okay, this is n. That's modulus is always there. Now let us do this. So how many points? We can say that there are 4 points here. Alright. So let us see. This is 1 here. This is 2 here. So let us put it here 2. Okay. This is 4 here. This is 1 here. So this will become 4. Okay. This is 3 here. This is 2 here. So this will become 6. And this is 2 here and this is 1 here. So this will become 2 here. So now what is it we have done? The first step out of the 4 steps, we have done the time reversal here, then shifted the reverse signal, then we are multiplying. So what is now x3 of 0? How do I get x3 of 0 now? Now let us do summation. The final step is summation. So let's do the summation here. So let me just write here the summation. X3 of 0 is equal to 2 plus 4 plus 6 plus 2, that is 6 plus 6 12 plus 2 14. So we got this as equal to 14. Now what we do here is we just add one more circle here because we have to reference now. Now the second will be, this will be shifted by 1 minus n. When m is equal to 1, what will happen? M is equal to 1, this will become x2 of 1 minus n, isn't it? 1 minus n. So this we have to shift in the anti-clockwise direction by 1. This has to be shifted in the anti-clockwise direction by 1 time. That is, time shift will be 1. So what will happen then? Now this will move here. This will move anti-clockwise, isn't it? So this will move here, this will move here, this will move here. So what I'll do is I'll put this one here. So what this will happen? Now this will become what will happen here is, now this will become x2 of 0, that is equal to 1, okay, and this will become now x2 of 3 is equal to 4, and here this will become x2 of 2, that is equal to 3, and this will become x2 of 1 is equal to 2. Now x2 of 1 is 1, so this is 1, so this will become 1, okay, and this is 4 and this is 2, so this will become 8, okay, whereas this is 3, so this is 1, so we will get this as 3, okay, whereas this is 2 now and this is 2, so this will become 4, okay. So let us add this. So 8 plus 1, 9, 9 plus 4 plus 3, this becomes 12, okay. So this is 12 plus 4, this will become equal to 16. So let us add this, okay. So this is 4 plus 3 plus 8 plus 1 is 16. So we'll get the second one as equal to 16. So let us follow the same process. Next, what will happen when I take m is equal to 2, x2 will be equal to 2 minus n, okay, this will be n. So what we have to do here is, now this again we have to shift by one more step. So what will happen? This will come here, this will come here, this will come here, this will come here. So there will be a circular rotation. Circular rotation will happen here. Now when this is happening, then you will get a value for x3 of 2 and then x3 of 3. So on the same steps we follow, we will get the answers as follows. Okay, let us, after doing all this whole process, I will get here 14 and I will get here 16. This is what we have done. So the same steps we are following, we are shifting them, the whole thing is shifted. Then all those 4 steps we are following, then x3 of 2 we are getting it as 14, x3 of 3 we are getting it as 16. The answer now is x3 of n, this is what we have to get, x3 of m, sorry. So what are the values we got? The first one is 14, second one is 16, the third one is 14 and the fifth one is 16. So this is the answer after calculating the circular convolution of x1 of n, x2 of n of a sequence. So this is how we calculate. Let me just summarize what we have done. So what is it we have done? The first step is we are plotting the points given in a circle. So take a circle, plot x1 of n, x2 of n in the anti-clockwise direction. That's what we have done. The second is we start with m is equal to 0, the first point. Then x2 of n will become x2 of minus n. So x2 of minus n reverse. So draw another circle and now draw the points in the clockwise direction. Okay, so they'll get x2 of minus n. And the next one will be x2 of 1 minus n, that will be time shifted by 1. So what happens now, the next time when you do that, you put this in the reverse direction, again anti-clockwise direction. So that will move in the anti-clockwise direction. After you do that, once you multiply by the x1 of n, which is not shifted, then you'll get a product, add those product, then you'll get this number. Similarly, next time is shifted by 2, that means the previous one is shifted by 1. Okay, Like that is do this, then you'll get an answer which is equal to the final result after circularly convolving. So we have in fact taken all the steps. So what are the steps here? First we have plotted, then we have folded, that is we are taking it x of x2 of minus n, that is the time reversal. Then we are shifting the reversed signal, isn't it? The reverse sequence we are shifting it, so that's what we have been doing. Then finally we are multiplying with x of n, and then last to get the answer we are adding them all. So this is how circular convolution is done. Let us see the second example. What does the second example say? The second example says, find the response of an FIR filter with an impulse response given as h of n is equal to 1, 2, 3, that is the sequence, to the input sequence x of n is 1 of 2. That means we have to find out what is y of n. What is y of n? When x of n and h of n are given. Okay, so you have the summation formula where you take, isn't it? Y of n is equal to summation x of n, h of shifted, isn't it? It is shifted again, x, h, isn't it? So that convolution, that summation you have to do. Now I'll show you a graphical, a matrix method which gives us an easy answer. So when I convolve these type of signals, okay, what is n for this? Let us say this is n1 is 3 here and n2 is 2 here. So the sequence of the output n will be equal to, n is equal to n1 plus n2 minus 1, that is 3 plus 2 minus 1, that is this is 4. So that will be the final sequence of your answer. Now I'll show you a graphical or a matrix method, not a graphical method. I'll show you a matrix method which helps us in calculating this type of responses very easily. So let's draw this here. Okay, let me show you this. Okay, let us take this as h of n and this is a x of n. So what is the sequence x of n given here? 1, 2 here. What is the sequence here? 1, 2, 3. Okay, let us multiply this. 1, this is 2, this is 3. Okay, this is 2, this is 4, and this is 6. Okay, so let us write down. This will add this, will add this. Okay, so what will be the y of n? The y of n will be, the first sequence is 1, the second is 2 plus 2, that is 4, the third is 4 plus 3, that is 7, and the fifth is 6. So we write like this. This is the sequence which we will get. Okay, so this is the sequence. So what is it we have done here? I'll just show you again. What is that here we have done is, we have multiplied this, we have put it here, then this we have written there, these two we have added, these two we have added, and the final one there is no addition, so it has to happen here. So this is 1, this is 2 plus 2, 4, this is 4 plus 3, 7, and this is 6. So this is the how you get the response of a FIR filter given the impulse response and also the input sequence. When I know these two, you know y of n will be convolution of these two, that is summation. Okay, so we got this using this matrix method. Let's see the next example. Okay, well now we have to find the DFT, discrete Fourier transform, of a given sequence. X of n is equal to 1, 1, 0, 0. So what is given for us? It is given that the length of the sequence n is equal to 4. Okay, so that's the length which is given to us. Now let us write down the formula first, how to calculate this, and then let us do it without doing any errors. Let us try to do without any errors. So let's start. How do I find the discrete Fourier transform? That is given by x of k is equal to summation, okay, n is equal to 0 to n minus 1, okay, then x of n e to the power of minus j2 pi n k by n. So this is the formula for us. Now in this we can just simplify this a little because I know what is the value of n. So I can just rewrite this again. So for us n is equal to 0. So this is 4 minus 1, that is 3. So let us write here. Then I'll write here x of n is equal to minus j2 pi n k by 4, that is our n. So this is the formula which you are going to use throughout the case. Now what is the sequence length? N is equal to 4. So I'll start with k is equal to 0, k is equal to 1, k is equal to 2 and k is equal to 3. So k is again from which place to which place? Let us put down here k is equal to 0, 1 up to n minus 1. So here also k will be equal to 0, 1 up to n minus 1. So for us there are 4 values of k because k is 0, k is 1, k is 2 and k is 3. So let us look at this problem in that respect and let us start solving this. So let us take the first case. What is the first case? Let us take that case here, case 1. Okay, when k is equal to 0. Let us start with k is equal to 0 because that's what it says. So we have to start with 0. Now I will find out x of 0 first. This is x of k. Now k becomes 0, so this will become x of 0. So what I'll do is I'll write down here x of 0. Okay, then summation will be what? This will be n is equal to 0 to 3 x of n, and here n being 0, this is value 1. So I'll just put it here x of n only. So now let us expand this. So what I'll do is I'll expand this. I'll say this is x of 0, n is equal to 0 plus summation, isn't it? X of 1, the second case, plus x of 2 plus x of 3. So how much is this? This is equal to x of 0 is how much here? 1. X of 1 is how much? 1. Okay, x of 2 is 0. There is 0 here and this is also 0. So what I'll get is I'll get x of k, that is x of 0 is equal to. Let us put it somewhere there. So we'll put it here. I'll write down here x of 0 for us now is equal to 2. Is this visible when I move there? Is it visible in that camera? This one, x of 0 is equal to what I have written. Now let us take the case 2. What is case 2 now? What is case 2 when k is equal to 1? We already seen what is k, what is the value of x of k when k is 0, that is x of 0. Now let us look at the second case where x of k will be equal to x of 1. What will be its value? Okay, let us again write. So what I'll write here is x of 1 I'll write. So let us write down what is x of 1. So x of 1 is nothing but summation of n is equal to 0 to 3 x of n a to the power of minus j 2 pi n. And what is k for us now? So k we can put it as 1 here. This k is equal to 1 by n. Okay, in fact this is now equal to n is equal to 0 to 3 x of n e to the power of minus j 2 pi n by 4 because k is equal to 1. So let us put that here. Now let us expand the summation. So expanding the summation, what I'll get here is let us write down here is equal to, first of all, x of 0, absolutely no problem because you can just write like that. Then comes x of 1 a to the power of minus j 2 pi. Now n is also equal to 1, so that will be minus j 2 pi by 4. Okay, plus x of 2 e to the power of minus j 4 pi by 4 because now n is equal to 2, so that will become 4 pi. Then comes x of 3, okay, e to the power of minus j. What is n now? N is equal to 3, so it will be 6. 3 into 2, 6, 6 by 4, that is equal to 3 by 2. So I can write this as minus j 3 pi by 2. Now as you're aware, if you look at the sequences, this is actually equal to 0 and this is also equal to 0. So let us look at the other case now. So this is what is of importance. X of 0 as you see here is 1. So well, let me put 1 here. Plus x of 1 is again 1. Okay. And this is equal to e to the power of minus j pi by 2. Right. This is equal to e to the power of minus j pi by 2. Now, I'll expand this using Euler's theorem. So I'll write this like this. 1 plus cos pi by 2 minus j sine pi by 2. Okay, cos 90 is 0, sine 90 is 1. So this I can get it as equal to 1 minus j. So now what I'll do is, I'll write this value. What is my x of 1? So I'll write down x of 1 here is equal to 1 minus j. So that's where we have written. So x of 1 is equal to 1 minus j there. Let us look at case 3. So what is case 3 for us? Now case 3. is k is equal to 2. We have seen k is equal to 0, k is equal to 1, now k is equal to 2. So let's start this. Again, let me write the formula. So this I can write as x of 2, that is equal to summation n is equal to 0 to 3 x of n e to the power of minus j 2 pi n. Okay, k for us now is 2. So I'll write here is 2 by 4. Okay, in other words, I can write this as summation n is equal to 0 to 3 x of n e to the power of minus. Now we can actually, see here, this is 2 pi n into 2. So this 4 pi, 4 and 4 get cancelled. So I can just write this as j n pi. Simple. Now there is no denominator because the denominator and numerator get cancelled each other. So 4 is gone. So this is minus j n pi. Now let's expand this again. So what I'll do is, I'll write here x of 0. Okay, let us write that here. X of 1 e to the power of minus j pi, isn't it? Because n is 1. Then comes x of 2 e to the power of minus j. N is 2 now. So this will become j2 pi plus x of 3 e to the power of minus j3 pi. As you see here, this doesn't exist, this doesn't exist, because for us x2 and x3 and x3 for us are given as equal to 0. So those are removed now. Now let us concentrate on this. So this, as you are all aware, this is 1 plus now this is again e to the power of minus j pi and x. I can write it as cos pi minus j sin pi. Okay. So cos 180 is minus 1. So this will be 1 minus 1. So this will be equal to 0. So x of 2 for us is 0. Okay. Now let the camera move on to that side. I'll write the on the top there. So this is now x of 2 is equal to 0. Let's take case 4, the final case. So this is case 4. Okay. K is equal to now 3, 0, 1, 2, 3. Now let's write again x of 3 here. X of 3, as you are aware, this will be equal to summation n is equal to 0 to 3 x of n e to the power of minus j2 pi n into k is equal to 3. So this will be equal to 3 by 4. Okay. So this I can write as summation n is equal to 0 to 3 x of n e to the power of minus j 2 to get cancelled there. So actually, in fact, we would have cancelled it here, but we want that 2 pi to remain in our case, so that the flavor remains. The formula which we don't want to forget the formula. So in the formula, invariably 2 pi is there. So we thought we'll not disturb that. In fact, you can simplify it here itself, right? Let the flavor remain so that you remember that formula forever. Okay. Now let us see. Now I can actually do some cutting here. So this will be 3 pi by 2. So I can write this as minus j 3 pi n by 2. So, okay, this 3 remains because k is 3 for us. So, these 2 to cancel. So, we have 2 there, and then this pi is there. So, 3 pi n by 2. Let us expand this, how it goes on. So, now, again, let's start with x of 0 plus x of 1 e to the power of minus, now n is equal to 1. So, that will be minus j 3 pi by 2. Okay, 3 pi by 2 plus x of 2 e to the power of minus, now n becomes 2, so 2 gets cancelled. Okay, so we can write this as minus j 3 pi plus x of 3 e to the power of minus j 3 into 3, that is 9 pi by 2. So this will be equal to 9 pi by 2. Now again, using this earlier how we have done, so this will be 1, this will be j, so this is equal to 1 plus j. So let us again move the camera there so that I can write the value there. So now what is x of 3 for us now? X of 3 is 1 plus j. Now we got 4 values of x of 3. That is, we have ultimately calculated the discrete Fourier transform or DFT of a given sequence. So given sequence was there, we got a sequence x of n here, and finally we have calculated x of k. Let's put all of them together. So I can write it in this small space here. So x of k, I can write it here as, what is the first one? 2, 1 minus j, 0 and 1 plus j. So this is our x of k, which is nothing but the discrete Fourier transform of a given sequence x of n. So we got this answer. So remember, you write as it is, 0 also there, you should put 0 also there. So the sequence length remains same. In fact, we can also add. When I add all of them, then what will happen? 2, 1 minus j plus 0, you will get the answer as 4. So when you do the addition also, you can get the answer x of k. Okay. Let us see the next example. In this example, we are doing exactly inverse of what we have done earlier. Earlier, given a sequence x of n, we have calculated the DFT x of k. Now in this problem, given a DFT, we have to find out its sequence, time sequence. So I have to find out IDFT, that is inverse discrete Fourier transform. So let's look at y of k is given as this. This is the problem. Problem is y of k is given as 1, 0, 1, 0. Okay, so what is given for us? Obvious, the length of the sequence is 4. Then we also know what is y of n. Y of n is nothing but inverse DFT of y of k. What is this formula for this? This is given as 1 by n. Again, k is equal to 0 to n minus 1. X of k e to the power of j 2 pi n k by n. This again is the same formula, except that there is no minus sign in the exponential. So this is how we get the y of n. Now as you are aware, n is equal to 4. So let us rewrite this equation. So I will write down here y of n is equal to 1 by 4. That is what we know. The summation is equal to k is equal to 0 to 3. Okay, x of k e to the power of j 2 pi n k by 4. Okay, where n is equal to 0, 1, so on up to n minus 1. So what is n minus 1 for us? 3. So I should calculate what is y of 0, y of 1, y of 2 and y of 3. So again, what we have done earlier, we are doing it in the reverse process. So let us start all those 4 cases. Let's look at the 4 cases and do this problem. Okay, case 1 again. Okay, y of 0, that is when n is equal to 0. So let us write down that. So this is equal to, now y of 0 for me is equal to 1 by 4, k is equal to 0 to 3, x of k. Okay, now this becomes exponential to the power of 0. So this will be just of x of a. Let us write down this. So I can write this as 1 by 4. Let us start with x of 0 plus x of 1 plus x of 2 plus x of 3. So how much is that? So all this is equal to 1 by 4 of x of 0, if you look at, is 1, next is 0, next one is 1 and next one is 0. So this is equal to 2 by 4, that is equal to 1 by 2. Let's move the camera a little there so that I can write down y of 0. So what is y of 0 here? Let me just put out here. Y of 0 is half, which we have put there. Y of 0 is half. Let us take case 2 now. Case 2, n is equal to 1, because already we have seen n is equal to 0 there. So let us write down this. So this will be y of 1 now. Okay. So again, let us write down the whole formula. K is equal to 0 to 3. Okay. X of k. And now e to the power of j, n is equal to 1. So this will be equal to, okay, this is 1. So 2 pi k by 4. So 2 to gone. So this I can write as pi k by 2. Okay. So we have done that, division here. So 2 by 2 is 4. So this is 2 here. Pi is n is equal to 1. So we got this. Now let us expand this summation. Simple. So let us just write down there 1 by 4 here. And then let us write down x of 0 for us first, then comes x of 1 e to the power of j pi by 2 plus x of 2 e to the power of j pi. K is 2 now, so 2 gone, so this will become j pi plus x of 3 e to the power of j 3 pi by 2. So this is our expansion. So let's recheck this again. X of 0, x of 1, k is equal to 1, so this will be j pi into 1 by 2, that's j pi by 2. X of 2, k is equal to 2 here, so e to the power of j pi into 2 by 2, so that will become j pi. X3, k is equal to 3, e to the power of j pi into 3, 3 pi by 2. Okay, so now let us write down this expansion. X of 0 for us is 1, so let us put that 1. So this is 0, so this term cancels. And then what about this? X2 is 1 again. So 1 into e to the power of j pi, okay, and then that other term is gone because that's also equal to 0 now. So I can write this as 1 by 4 into 1, okay, that is the j pi will be minus 1, so this will be equal to 0. Let's just shift the camera a little there. So y of 1 is equal to 0 for us here. Y of 1 is equal to 0 here. Let's see the case 3, n is equal to 2. Now that means now I'll write again y of 2. Okay, so this will be equal to 1 by 4 summation k is equal to 0 to 3 x of k e to the power of j 2 pi, and then for us n is equal to 2, so I write this as into 2 into k by 4. So this is nothing but, you know, this gets cancelled, so it will be e to the power of j pi k. Okay, let us expand that. So let me write here 1 by 4. Okay, so this I can write as e to the power of j pi k. So let us put that here for our clarity. So now x of 0 first comes, then comes x of 1. Okay, so that will be e to the power of j pi, remains as it is. Then comes x of 2 e to the power of j 2 pi plus x of 3 e to the power of j 3 pi. Okay, let's just simplify this. So this will be 1 by 4. This is 1. Okay, 1 into e to the power of j 2 pi. Okay, now this will be equal to 1 by 4 into 1 plus 1. So this is equal to 1 by 2. Now what is the value of y of 2? Y of 2 is for us is half. Okay, so let's go there. Y of 2 is equal to half for us now. Let us see the next case, that is case 4. What is case 4? Case 4, n is equal to 3, that is I am going to calculate what is y of 3. Let us put there again the formula 1 by 4 summation k is equal to 0 to 3 x of k, now e to the power of j. Okay, for us n is equal to 3, isn't it? So 2 gets cancelled, so this will be j 3 pi k by 2. Okay, that is what we are going to put there. Now let us expand this again. So let me write down how much is this. So this will be 1 by 4. Okay, then start with x of k, that is 0 first of all. Then comes x of 1. Then what will be that? That will be e to the power of j 3 pi by 2. Then comes x of 2 e to the power of j 3 into 2, that is will be equal to 3 pi, okay, plus x of 3 e to the power of j. Now pi is how much? K is how much? 3. So 3 into 3, 9. So this will be j 9 pi by 2. Okay, so now let us expand this. Now in this, as you are aware, this term is not there, this term is not there because they are zeros here. So I can write this like this: 1 by 4, x of 0 is 1, okay, this again is 1, so this is e to the power of j 3 pi. Okay, now after expanding this, you will see that this is equal to 1 by 4 into 1 minus 1, that is equal to 0. So let's move there. Let's move a little. So this is y of 3 for us is equal to 0. So from this we have seen that we have calculated the inverse discrete Fourier transform of a given discrete Fourier transform. So in that case here, as you see here, y of 0 is half, y of 1 is 0, y of 2 is half, and y of 3 is 0. So this is the inverse discrete Fourier transform of a given sequence, which is in terms of y of k. Okay, in this session we have seen what is circular convolution property of a DFT. We have understood what exactly circular convolution, how exactly a circular convolution can be calculated for a given sequence. So how did we do? Let us just quickly recollect what we have studied. We have taken two DFT series, x1 of k and x2 of k, both of endpoint length. Then if the product of these two, let us call this x3 of k, which is again a DFT. So that is x3 of k is nothing but x1 of k multiplied by x2 of k. That means we are multiplying two DFT sequences. So as per the circular convolution property, this is equal to, or x3 of m, which we call it as a circular convolution of these two, that is x1 of n, and then we put a capital letter in between, so indicate circular convolution. So x1 of n circularly convolved with x2 of n will have, as per the property, will have x1 of k into x2 of k. So as from the session which we have studied, we have seen that x3 of m can be written in the form of a summation of series, where x3 of m is written as summation n is equal to 0 to n minus 1, x1 of n multiplied by x2 of m minus n of mod n. So this is the difference between a circular convolution and a linear convolution. That's why this is called as a circular convolution. So we have seen also how to plot this on a graph, or in a circular graph, or put it on a circle, and then we have seen how it can be shifted. So there are four basic properties of circular convolution, how to calculate them. First of all, I have to calculate the time reversal. Then I have to calculate what is the shifting of this. Then comes the multiplication. Then finally comes the summation. So all these points we have put together and we have solved in fact one problem. Later on we have solved some problems on DFT. In fact, we have seen a few problems. One is a wonderful method with a very shortcut method, which you have seen a matrix representation, where I have calculated the response of an FIR filter just like that. Given h of n and x of n, any series, you can just put that. And also one important point which I want to tell you here is, when I want to calculate a circular convolution of that, we have calculated y of n, isn't it? Y of n in fact can also be calculated using circular convolution. So we have calculated the total length of n. So n is n1 plus n2 minus 1, that's we have calculated. And then we have to do what is called as a padding with zeros if I want to calculate the circular convolution in this particular case. That means if there are only h of n, let us say there are only sequences given. So what I'll do is, if the total length of the resultant is 4, then I'll add 2 more zeros to it. Similarly, x of n, that is input, also I will do the same case. That means I'll also pad with zeros. When I do this, in fact, I'll get a sequence, okay, which is similar to how I have calculated. So this is what is called as a padding with zeros. When I pad with zeros, then I use again the same circles, plot them, then find out what is minus of n first, then minus of n shifted, 1 minus n, 2 minus n, 3 minus n, like that up to m minus n we have to calculate. Then we have to add up. Then finally we'll get a result which is this circular convolution. So if I don't add zeros as padding, then the answer will be a little different from the earlier one. So this is what we have studied in this session.